Here, you're trying to find the functions f and g such that f of g, so f composed with g, is equal to the function h, where h of x is the square root of 64 minus 25x squared. And then the second one, which is here, we got f of x is equal to square root of x. G of x is equal to 9x plus 1. We want to find the following composite functions in the domain of those functions. So you got f composed with g, g composed with f, f composed with f, and g composed with g. So give those a shot, and get your brain warmed up, and then we'll go over them if I can figure out my computer. There we go. Oh. We're trying to find functions f and g such that f composed with g is going to make up that function h. Like I said before, there are infinite number of answers here, and so there's really a lot of answers that could be correct. We could talk about a few of them, but remember, if we're saying that f composed with g is equal to h, that means that f of g of x is equal to h of x. That means that g of x is an inner function. So what did y'all pick for g of x? 64 minus 25x squared. That'll work, right? And so if you choose that as your inner function, what's going to be the outer function? What's going to be f of x? The square root of x. Perfect. That'll work. There we go. Any questions on that? Now, there's more answers that you could have to this, just to give you some other options. You could say, well, I'll make g of x equal to 25x squared. And then in that case, f of x would be the square root of 64 minus x. So there's a ton of different ways you can do it. I just want you to understand how you can do it, and maybe what's the best practice or the easiest way, which I would say the one that you chose here, that's probably the easiest way to do that one. If you go into calculus, this is something that you'll use in one of the rules, and so that's why we teach it. Any questions on that? Oh. All right, let's go to this one. Ooh. So we got f of x is equal to the square root of x, and g of x is equal to 9x plus 1. We're trying to find the following composite functions and the domain of those functions. So define f composed with g. Remember, that's f of g of x. So that means everywhere there's an x in f, we're going to substitute in g of x. So this is going to be the square root of g of x. And then now we know what g of x is, so we're going to substitute that in. And so we're going to have the square root of 9x plus 1. There's not really anything I can do to simplify that. That is just what it is. You can't split up a square root or any root on addition or subtraction. So you can't just do the square root of 9x and try to evaluate that. So that's as far as you can go. Let's talk about the domain. So if we're talking about the domain of this function, first thing we need to do is look at the domain of the inner function, which is g. And you look at the domain of g. If we look at g, are there any domain restrictions on that? Why not? We don't have a variable in the denominator. We don't have a variable under an even root. You just got 9x plus 1. So the domain of g is just negative infinity to positive. No restrictions there. Then, next we want to look at the domain of the function we found. For our composite function, it would be 9x plus 1. Oh, sorry, square root of 9x plus 1. Square root is pretty important. Is there domain restrictions on this? No? Can, huh? What? It's at the top, but it's under an even root, right? It's the square root. And so we know that stuff under the square root, the 9x plus 1 has to be what? Anybody know?
Oh, it can't equal 0.
It can equal 0. It also has to be greater. Greater than or equal to 0. Can't be negative. You take the even root of a negative number, we're in imaginary number territory, and we're not talking about that. We're strictly talking about reals.
So only when it's under a square root, that's the only time you make it greater than equal to 0?
Yes. If it was a fourth root or a sixth root as well. So any even root.
So what if it's under a third root?
Then you don't have to worry about it.
Oh.
Mm-hmm. Those can be negative. So we just got to solve that up. Track 1 both sides. We got 9x greater than or equal to negative 1. And we'll divide by 9. So x is greater than or equal to negative 1/9. So we got one domain. It could be anything. The other domain, it has to be greater than or equal to negative 1/9. We combine those restrictions together, and so the domain of f composed with g is going to be, kind of mixed up what I was doing there. Come on, there we go. X such that x is greater than or equal to negative 1/9. That's going to be our domain.
You don't combine them together?
What's that?
You don't combine them together?
Well, we are combining them, right? One of them is, it could be anything. The other one is saying it has to be negative 1/9 or above.
So it's going to be the bracket negative 1/9 to positive 2?
If you want to write it that way, you can. I don't know how they ask you in the homework, actually. Maybe else be worried about that. Any questions on that? Nope. All right. What's next? G of f. Golf. So remember, G composed with f. It's the same thing as G of f of x, which means that we're going to take G, and everywhere there's an x, we're going to put f of x. So G is 9x plus 1, so it's going to be 9 times f of x plus 1. And then we know f of x is the square root of x. This is going to be 9 times the square root of x plus 1, which we can't really do much with that. So let's just keep it as 9 times the square root of x plus 1. The domain?
Oh, no, because it's the square root.
Ah, yeah. Oh, I had it written right there. All right. So let's try to figure out the domain. So what are we going to look at first? The domain of f. Good. The inner function. And so f was the square root of x. So if you have the square root of x, what's going to be the domain for that? Yep. So that's that domain there. So from 0 to infinity, including the z. What are we going to look at next? Talk about the domain of this 9 times the square root of x plus 1. Okay. function that we found is our composite function. And so what's the domain of that going to be? Yeah, but what's going to be greater than or equal to 0? Remember, it's just the stuff that's under the root. So what's under the root? It's just x. So once again, we get x is greater than or equal to 0. So if we combine those together, the domain of my composite function is going to be what? 0 to infinity. Yeah. That's all there is to it. So if you get the same domain for both the inner function and the composite function, when you combine them together, it's just going to be the same thing. Any questions on that? All right. F of F, FOF. So remember that is F of F of X. That means everywhere there's an X in F, we're going to put another F of X. So we're going to have the square root of F of X. Which F of X is also the square root of X. So we're going to have the square root of X. Can we simplify that in any way? There you go, good. So it's going to be the fourth root of X. And that's going to be our composite function. I think we did that one yesterday. On one of the days. Who knows? All right, let's talk about domain. So first we're going to look at the domain of what? Of F, which that is the square root of X. So that's going to be X is greater than or equal to 0. So we got that restriction we're going to have. And then we need to look at the domain of the fourth root of X. That's going to be the same thing. Yep, because it's an even root with the X side of it. So this is just going to be X is greater than or equal to 0. And so the domain of my composite is going to be those two combined. So 0 to infinity, including the 0. Any questions on that one? And G of G. So G of G, remember it's going to be the same thing as G of X. So everywhere there's an X in G, we're going to put a G of X. So it's going to be 9 times G of X plus 1. I think that's what the function was. Yep. And then we're going to replace that G of X with 9x plus 1, what it is. So this is going to be 9 times 9x plus 1 plus 1. You've taken the function and put it inside itself. And we can simplify this a little bit. I can distribute the 9, go to the 9x, also goes to the 1. And so this is going to be 81x plus 9 plus 1. And, oh, we'll have room that way. So let's go this way. So 81, oh, yeah, that's right, 81x plus 10. That's going to be our composite. Any questions on that? Nope. All right, let's talk about the domain. So what's the domain we're going to look at first? Domain of G, that's our inner function. And what's the domain of G? Negative infinity to positive infinity. There's no x in the denominator. There's no variable under an even root. So there's no restrictions on the domain here. Next, we're going to look at the domain of the function we found. Are there any restrictions there? No, it's 81x plus 10. So no variable under the denominator, no variable under even root, no restrictions. So the domain of my composite function is going to be negative infinity to positive infinity. Any questions on any of those? Nope. I do have one kind of what if. So, what if you have a function f and that's the square root of x? And when you do f composed with g, oop, actually wrong way, g composed with f is what I want. You end up getting, yeah, so let's do yes, that's what I want. And we want to find the domain of g composed with f. What are we going to look at first?
The square root of x minus 4.
No, remember?
We were looking at the square root of f first.
Yeah, you want to look at the domain of the inner function, which in this case is f. So I want to find the domain of the square root of x, which is going to be what?
X cannot equal zero. I'm not x is greater than equal to zero.
X is greater than or equal to 0. Okay. And then after that, we're going to look at the domain of the function we found, which is 3 over square root of x minus 4. How do we find the domain of that one?
X minus 4 is greater than equal to 0.
Okay, so there's one problem with that.
But it can't equal 0 because it's greater than
Yep, perfect. This is in the denominator, it can't equal 0. Then we want to make sure it's just strictly greater than 0. We're going to solve that up. We're going to run out of room, and we're going to get x is greater than 4. So, question on finding that first off. How are we going to combine x is greater than or equal to 0 and x is greater than 4? What do you think I'm going to write my domain as?
Would you put the 0 but just not include?
No. So let's say we got a number line, right? And for f, we're saying that it's greater than or equal to 0. So it could be equal to 0 and everything right there. For the 3 over square root of x minus 4, we're saying that it just has to be greater than 4. What's here? Which one is more restrictive? The 4. And so when we combine together, we combine those restrictions together, we're going to use the most restrictive domain. So this one includes 1, 2, 3, 3.5, 2.5, 1.5, all these numbers that can't be in this one. So we want to choose the most restrictive one. That is going to be our domain. So the domain of g of f is going to be from 4 to infinity. Any questions on that? That was the problem that sometimes confuses people. That's what I want to. And I don't know if you even see one like that, but it's just a topic that I like to go over because it can be a little confusing. Any questions? Nope. All right. Any questions on 6.1 composite functions? What are we doing with time? We got about 25 minutes. All right. Well, let's see if we can start. There's some 6.2 stuff. It's kind of split into two sections, so two parts. So I think we could do the first part today. So 6.2 is kind of a continuation. Well, no, it uses 6.1 stuff a little bit, so it's not really a continuation. But 6.2, we're going to talk about one-to-one functions and inverse functions. All this stuff kind of leads down the path to get us to exponential and logarithmic functions. But the objectives for this, we're going to determine whether a function is one-to-one. We're going to look at that today. Determine the inverse of a function defined by a map or a set of ordered pairs, and obtain the graph of the inverse function from the graph of a function, and find the inverse of a function defined by an equation. We'll probably look at these tomorrow. I just want to kind of focus on the one-to-one stuff today. So let us talk about, let's go for it. What makes a relation a function? Let's try to go back in time and think about when we talked about that. Does anybody remember what makes a relation a function? Or a function is just a special type of relation. You can do the vertical line test, yeah. But like, what's the underlying reason that the vertical line test tells us that? You remember?
The same input can have the same output.
You close.
It's like, I know what to say, I don't know how to word it.
One input can't map to two outputs.
Yeah.
Or let's say more than one. More than one output. Okay. So that means if you have an x value, it should only be mapped to one y value. Okay. If you have an x and it's mapped to like a y sub 1 and a y sub 2, that is not a function. Okay. And there was this type of problem that they would use to try to confuse you, where they would set up the mapping and they would have let's do some color here, x sub 1 and x sub 2, and they would have that mapped like so. And we would say, is that a function?
Well, yes, it is.
It is, because x sub 1 is only mapped to one value, just the y sub 1. X sub 2 is only mapped to one value, the y sub 1. Even though they're mapped to the same output, the same y value, it is still a function. Okay. One-to-one functions are functions where that is not true. So a function is one-to-one if any two inputs in the domain correspond to two different outputs in the range. So that is, if x sub 1 and x sub 2 are different inputs, then their y values, f of x sub 1, not equal f of x sub 2. So basically what it's saying is, if you look at these right here, every x is mapped to one unique y. Here, x sub 1 and x sub 2 are both mapped to y sub 1. That's not 1, 2, 1. This one is not even a function, right? Because x sub 1 is mapped to two different values. It's ambiguous with the output. So that one's not even a function. It's a relation. So the way that I like to word it, if I have some room to write it, there we go, is a one-to-one function. Now let's just shorthand it. Has every input mapped to a unique output. And that's what makes it one-to-one. It makes sense. I mean, it's in the name, 1, 2, 1. That one x is mapped to one y. There's no other x mapped to that y. 1 to 1. I just thought of an example with basketball, but I don't know, it might be. But if we look at these graphs, I mean, we talked about them earlier, but we'll go back over them again. But each value in my input here is mapped to a unique output. None of them share an output. Sorry, thank you. So this is a one-to-one function. In this one, you have x of 3 is mapped to a unique output, but x of 1 and x of 2 are not mapped to unique output. So that is not a one-to-one function. It is still a function, but it is not a one-to-one function. Any questions on that? All right, so let's look at some examples here. So this is A. It has age and HDL, which is good cholesterol. I don't really know. And so you have their ages mapped to the HDL cholesterol. Is this a function, first off?
It's a function, but not a one-to-one function.
It is a function. You're saying it's not one-to-one? And why are you saying it's not one-to-one? These two are mapped to the same output. So each x does not have a unique output. So yes, this is a function, but it's not one-to-one. Any questions on that? What about this one right here? It's a relation written out through order pairs. So -2 is mapped to 6, -1 is mapped to 3, 0 is mapped to 2, 1 is mapped to 5, and 2 is mapped to 8.
It's a one-to-one function.
That is a one-to-one function. Every input is mapped to a single output, or not even just a single output, a unique single output, right? Any questions on that before I go? Keep going. If I wanted to make this not a one-to-one function, what is one thing I could change to make that so?
You could make, like, the -1, you can make that output 6.
Yep. So, well, let's not write it over. But if I wrote -1, it's mapped to 6. That would mean that -2 is mapped to 6 and -1 is mapped to 6. And so this would still be a function, but it would not be one-to-one because you'd have two inputs mapped to that one output. They would share an output. Any questions on that? Let's see. You got the state and the population in millions. That's probably not right anymore. But is this a one-to-one function? Yeah, this is a one-to-one function. Each element in my input is mapped to one unique element in my output. So this is a one-to-one function here. And let's look at this one. No, so this is not, it's a function. Yeah, but it's not one-to-one. Because you have both dog and cat are both mapped to 11. Duck, lion, and pig both mapped to 10. And rabbit is mapped to, well, the rabbit one doesn't matter at all because nothing else is mapped to 7. Is that really the life expectancy for dog and cat? I thought it'd be higher than that. Any questions on that? All right. Let's go. Okay, so We use the vertical line test to tell if a relation was a function based off the graph to see if a function is a one-to-one function. We can use the horizontal line test, because if you have two different inputs, two x's with the same output, their y values will be the same. And so if you can draw a horizontal line that intersects the graph at more than one spot, it is not a one-to-one function. Any questions on that? So it's the same as the vertical line test, where if you, I think I did it like this for y'all. How did I do that? We would take the vertical line and make it go all the way across like a radar. I always think of it as radar, sonar. Well, you take this, you go up, and it will say we come down. And it's fine now, but boom, once we get here, I intersect that graph at two spots, and so this fails the horizontal line test. Any questions on that? Now, what that tells us is a constant function one-to-one?
No.
Why not?
Oh, yeah.
Huh? What do you think? What does a constant function look like?
Oh, no, it's not. It's going to be a straight line.
Yeah. So a constant function, all the values of x will have the same value for y. So a constant function is not one-to-one. And so what we can think about is, as x is changing, the y value must be changing as well. And it can't change the way that it's changing. If it increases and then decreases, boom, you're going to have a point where the y values are the same. And so that leads us to this right here. A function that is increasing on an interval I is a one-to-one function on I. So if it's always increasing on an interval, it's going to be one-to-one. A function that is decreasing on an interval I is a one-to-one function on I as well. And so if a function is strictly increasing or strictly decreasing, I think I talked to you about the word, it has monotonicity. So it's not changing if it's increasing or decreasing, then it is a one-to-one function. Now, there is, I guess that was not a function, so we don't have to worry about it. Yep. I was thinking of a vertical line, but a vertical line is not a function, so we don't have to worry about it. So basically, for it to be one-to-one, and it doesn't have to look like this exactly, but it always has to be increasing or decreasing. I mean, it could change the rate at which it's increasing or decreasing, but if it ever goes to constant, it's going to fail the horizontal line test. Or if it ever switches to decreasing from increasing or decreasing to increasing, it's going to fail the horizontal line. Any questions on that? All right, so let's look at some examples. Did I draw them here? Yeah. So this first graph here, that is x squared, and then this is x to the third. And so you can see the graph, we talked about quadratic functions earlier. It has that parabola shape. Any quadratic function, unless you limit the domain, is not going to be one-to-one, because it's always going to either increase and then decrease or decrease and then increase, right? That's the basic shape of it there. And so you could draw any horizontal line that doesn't just go through the vertex is going to intersect it more than once. So this function right here is not one-to-one. If we look at g of x is equal to x to the third, every horizontal line I draw is only going to intersect it at one place.
At the origin, it looks like it.
So that's what I was about to go to. So it looks like it may right here, right? But if we zoom in all the way, it still has a slight increase up to here and then increase away from there. So there's actually no place that it actually would intersect it at more. Any questions on that? No, oh, I made a little line to drag up. I forgot I did that. Now, let me make sure I don't have anything else here. Yeah, cool. Now, what about this function here? Because we just looked at x to the third. What if I do x to the third minus 3x, let's say plus 1, whatever. And I'm going to zoom in a bit for y'all. How did I do that? Oh, this. Oh, too much. Would you say that this is a one-to-one function?
No.
Why not?
Because they take the thing 3 times.
Yeah. So, I mean, if you just look at like the line y equals 2, boom. Intersects it once, twice, 3 times, not a one-to-one function, right? So, so not all of the functions that are similar in form like that. Other one was a cube. It was a x to the third. This x to the third will not be one-to-one. And the main thing that's making it, does anybody know what the main thing that's making it not one-to-one is? Is the minus 3x. Yeah, the minus 3x is going to kind of mess that up. The plus 1 just shifts it up for you. So even if I took that away, I just kind of threw it in there. So you can see that will still intersect the line I drew earlier, still intersects it twice. So